Hello class, welcome to MEM4225, Advanced Products and Processes. Module 1, Queuing Systems and Manufacturing Simulation. Part 1, Background.
So the systems of focus in this module is called queuing systems. And queuing model is a mathematical study of waiting lines or queues, apparently from the name. So in queuing theory, a model is constructed such that the queue length and waiting time can be predicted. And we can think of various practical applications of queuing models. You go to a supermarket, you form a line. You go to a hospital, in the emergency room, you form a line. You call in the customer service, you basically have form a line there. Or you on the manufacturing floor, the line will be formed by the incoming outgoing parts, products, raw materials, orders, customer orders, and so on. There's a wide range of applications in various fields in our everyday life. The whole queuing theory has its origin from about 100 years ago of a Danish mathematician and engineer named Erlang. And the ideas have since seen applications, as I mentioned, in various fields. It starts all the way from telecommunications, but now it's used in traffic, engineering, computing, and service and manufacturing, and so on. Some historical note about the mathematician engineer Erlang. He majored in mathematics in the University of Copenhagen and worked in the telephone company in Copenhagen for several years. And during his work, he established this interest to study how many circuits are needed to provide an acceptable telephone service, and eventually this becomes the question of how many telephone operators were needed to handle given volume of calls. He developed the theory for telephone traffic over several years and derived and solved several simple queuing models. The one of them, MEM4225, we will see in this module as well. His paper has been since translated to various languages, and now his name is used for statistical distribution. We have a distribution called Erlang distribution, and it's named for a programming language as well. Now, for queuing models, the basic idea is shown in this diagram. Here, the circle and the queue represent different things. On the left-hand side, we assume there's a calling population or a stream of customers or jobs will enter the system on the left-hand side. Then, after the customers or jobs join the system, they will form a waiting line or a queue in the middle, and the server, which is the circle at the right-hand side, will pick up customers from the queue, provide a certain service or process the jobs, and the discharge or release the customer or the job after the service is completed. For a queuing system, the typical measures of system performance includes how busy the server is. This is what we call the server utilization. It's defined as the fraction of time that the server is busy. The busy means serving customer. And also we can look at how long does the queue can grow, or on average, how many customers are in the queue, or what's the fraction of time the queue has so many customers. And we can also look at the time performance. How long does customer has to wait? What's the probability has to wait for at least so much time? For simple queuing systems, as I mentioned, we can use analytical formulas to calculate all these performance metrics. But for more complex scenarios, these calculations are not possible. Now, for a given queuing system, the terminology in terms of queuing models, it's possible to find various ways to operate the system. So we have to make certain assumptions to confine the scope of our discussion. First, about the calling population, the population of potential customers that will join the system. In this particular module, in most cases, we'll focus on the case where we have infinite calling population, meaning you have a continuous stream of customers arriving into the system, and there's no upper limit of how many it can allow. Sometimes we want to study the case where we have a finite number of customers coming in. For instance, you receive an order to produce 50 units of certain products. Apparently, in this case, you have 50 jobs or customers arriving at the queue to be processed or to be served. Or, for instance, you have an international flight with 300 passengers coming into the airport, then you know there are 300 customers. In this case, the calling population can be finite. Okay? Or, like how many we have so many students in the class, so serving those students can also fit into this finite calling population scenario. Well, the main difference in various calling population scenarios will be the arrival rate. How many arrivals are we expect in a given period of time? In the infinite population case, the arrival rate in most cases are not affected by the number of customers who have left the calling population or have joined the queue system. But you have a finite population, then the arrival does depend on the number of customers. The more customers have arrived, the arrival rate typically will decrease. Now, the arrival process also requires some defining touch. For instance, if we have infinite calling populations, what we usually assume is the arrival process is characterized by their inter-arrival times. But arrivals doesn't have to be one by one. They can occur in batches of customers. And the size of the batch can be either constant or random in size. Of course, the simplest scenario is one customer arrive at a given any moment. And the basic model for random arrival is what we call the Poisson process. It is when the inter-arrival times between two customers follow exponential distributions. There are also cases where we have scheduled arrivals instead of random arrivals. And this is usually the case, for instance, if we look at hospital or clinic scheduling, where the patients are scheduled to visit a physician's office at a given time frame. Of course, even in the scheduled scenario, inter-arrival time can be constant or constant plus minus a small random amount. For instance, in the practical scenarios, even though we have a scheduled visit arrangement, patients or customers arrive at the facility, sometimes a little bit earlier, sometimes a little bit late. For arrival process, there is another scenario called unlimited arrival. This is the case where you have sufficient amount of jobs or customers waiting at the front of your queuing system. And whenever the server becomes available, the customer will be released to the system. And this can usually be used to model sufficient raw material supply at the beginning of the production line, in large volume manufacturing scenarios, for instance. Or some extremely busy hospitals. Now, after the customers have joined the queue, they may have different queue behavior. The simplest case is the customer will stay in the queue, don't move, and wait until it's turn to get served by the server. But sometimes the customer may leave when he sees the queue is too long. He may decide to not join the queue at all. Or in some cases, we say the customer is blocked by the queue. Other cases could be the customer leaves when the line is moving too slowly, when the queuing time becomes too long, for instance. And sometimes, if we have multiple queues, we may see customers move from one line to another line, one queue to another queue, if usually thinks that you can gain an advantage by, for instance, reducing the waiting time. And this is quite typical. For instance, when we drive our car on the highway in a traffic jam, we see cars changing lanes all the time. And we were waiting in the busy period of time at the supermarket lines. You may also choose to change from one counter to another just to save some waiting time. And in this particular module, we'll focus on the simple case where the customer will stay in the queue, no entering, no exiting as soon as he joins the system. But also we'll meet with one case where the customer may decide or may not be able to join the queue or be blocked or rejected because the queue is already reached its capacity. After the queue is formed, after customers have joined the queue and stay in the queue, discipline of the queue is also of importance. It refers to how the customers in the queue are ordered, who gets served first. Of course, the simplest case is first in, first out, FIFO. But in some applications, we may have other type of queue discipline. For instance, last in, first out. It's very typical in computer applications. Service can sometimes in random order. And maybe you choose to prioritize certain cases. For instance, you choose the job that has the shortest processing time. Right? You do the easy job first, and the more complicated, save the complicated ones or later. You may have a certain priority rule. For instance, when you buy things from Amazon, you can choose different shipping methods. Next day shipping, 2-day shipping, or week shipping, or those long 3 to 5 days free shipping. In those cases, you receive different priorities when being served by the warehouse, by the delivery, and so on. And a very different phenomena you can think of how these different queue disciplines are being used in the different application cases. Now, after queue is formed, after we know who will get served first, of course the server will decide how much time does it take for the service to be completed. And the service time, in our case, is usually assumed to be random and independently and identically distributed. Typical assumptions or distributions we use to model the service time include exponential distribution, gamma distribution, and Gauss-Erlang distribution. In practice, however, the service time may depend on the type of customer. Some requires more complex service, of course, in this case, longer time. Some will require simpler service, in this case, shorter time. And sometimes the servers tend to work faster than usual when the waiting line is long. Okay? So the service time in practice may also depend on the queue length in this case. And sometimes the queue system may consist of a number of service centers that interact queues. And the service centers can consist of several numbers of servers. They can work in parallel. In this case, the service time or the service rate can be greatly enhanced. But in this module, we focus on the simple case that you have independently and identically distributed service times. And sometimes it's possible to assume that you have an infinite number of servers. As soon as the customer enters the system, will get served immediately. But this is not the case that we'll focus on in this module. Now, in terms of the structure or the topology of models, several cases could be possible. The more complex ones will be what we call a fork join. At a certain point, the arrivals can split into two queues and eventually join either through assembly or through merge. Sometimes you may have several servers working in parallel. Like when you go to TMVs, you pick a number, and you have various servers, operators can help you. And sometimes things have to go in series. This is very typical in manufacturing process, where you have several manufacturing steps or process steps, and the material must go through all the steps before being released to the next department. In the first parts of this module, we'll only look at a single-stage queuing systems. And for single-stage queuing systems, there is a commonly used notation called the candles notation, the convention to denote various assumptions made to the system. It's usually represented by 5 or sometimes fewer letters. The first letter indicates the distribution of the inter-arrival time. The second letter indicates the distribution of the service time. The third one indicates the number of parallel servers. Since we have single-stage queuing system, we only have one stage, so the servers will all work in parallel. The fourth one indicates the system capacity. The system capacity is the sum of the number of servers plus the capacity in the queue. So if you have 2 servers working in parallel, and the queue can accommodate up to 5 customers, then in this case the system capacity is 2 plus 5 equal to 7. That's our system capacity. Finally, the last or the fifth symbol indicates the size of population. This is the total number of customers that will arrive in the system. Now, in some cases, as we mentioned earlier, the focus in this is mostly infinite calling population. In this case, k, the last one will be equal to infinity. And if that's the case, we don't have to write it into the notation. And if further on the system capacity is also infinite, you have infinite waiting room or queue size, then you can also ignore or omit that letter as well. So in terms of the distributions, we reserve capital letter M for exponential distribution, and M stands for memory release or Markov. We reserve capital letter D to denote deterministic or constant service time or inter-arrival time. And that EK represents the kth order Erlang distribution. And letter G is used to represent general or arbitrary distribution. When we don't have a specific distribution type, we use capital letter G to denote it. For instance, if we look at this MEM4225, which will be the first queuing system we'll study in the next part of this module, and represent a single stage queuing system with one server, and the inter-arrival time of customers follow exponential distribution. The service time also follows exponential distribution. Since we have 3 letters, it means the system will have infinite system capacity and infinite calling population. And when we have a queuing system, of course, it's necessary to quantitatively define all behavior or all features of such a system. And also, it's also important to quantitatively define the performance metrics that will eventually be measured or evaluated. The parameters include how fast the customer will arrive, or the arrival rate is in the unit of how many customers per unit of time. So it will be per hour, per second, per minute. And based on the arrival rate, it's possible to calculate the average inter-arrival time. So this will be the amount of time between 2 customers on average. And you can calculate by as the reciprocal or the inverse of lambda. And note that this average inter-arrival time calculated by this bears the same unit as the arrival rate, as the time unit in the arrival rate lambda. And similarly, we can define the service rate mu for the servers. It represents, again, the number of customers on average that a server can process or handle per unit of time. Again, it's be per hour, per second, per minute, and so on. And the average service time is 1 over mu, and again, it bears the same time unit as time unit in the service rate mu. If you evaluate mu in terms of how many counts per hour, the average service time in this case we calculate in units of how many hours. And of course, we can also define other parameters like the queue capacity and so on. Now, as far as the performance metrics are concerned, two types of performance metrics are possible or are available. One is what we call the long run or long-term steady state performance metrics. This is when you have the system run for a sufficiently long period of time and then calculate the long-term average of how the system behaves. And this will be the main focus of this module, and especially in the next parts of the lectures we prepare. So these metrics include, first, what is the fraction of time the server is busy? We call it the server utilization and use a Greek letter rho to represent it. We're also interested in the probability the server has a certain number of customers, for instance, n customers. We use Pn, or sometimes pi sub n, to represent this probability. And of course, n can be equal to 0, meaning you have the system completely empty, and you go to 1, 2, 3, 4, and so on. In terms of performance metrics, we can also focus on the average time a customer resides in the system, meaning from the moment it enters the system to the moment it exits the system. So this includes both the waiting time and the service time spent in the entire system. And we use capital letter W to represent the system residence time. Sometimes we only focus on the waiting time, which is a critical indicator of the service performance of a certain queuing system. And this is just the average amount of time the customer waits at the queue. Of course, the difference between W, the system residence time, and WQ, the queuing time, is the service time. On the other hand, we can also look at the queue behavior. In this case, we use notation L to represent the average number of customers in the system. This again includes the customer on the server, being serviced on the server, and also the customer waiting in the queue. So it's a combination of two, the sum of two. And again, if we only focus on the queue behavior, we define LQ as the average number of customers in the queue. This concludes the first part of this lecture, of the module. In the second part of the module, we'll discuss how to calculate these performance metrics for several types of basic simple queuing systems. Then in part 3, we'll discuss how to build a simulation model using the simulation software for those simple systems. Then along building this simulation model in the software, you can compare the mathematical formula result and your simulation result. And of course, if the simulation is created appropriately and correctly, the output should match the theoretical answers. This step is what we call the verification of simulation models, where you make sure the model is built the way you desire to be built. This is an important step since for larger systems, verification of the simulation model will become more and more challenging. Therefore, we want to make sure that everyone can build the correct simulation model by these simple exercises. This is the end of this module, of this part of the lecture.